Okay, let's see. Okay, good afternoon, everyone. I hope you had a nice lunch break and you are now full of energy for the next session or sessions. Thank you for the introduction. As already announced, I am Lukas Rybok from IONOS, and I'm really proud to be here on stage at the Bitcoin Quantum Summit together with the CTO of QMware, Georg Gesek. And for me, I must say I may not look that old. However, I already have more than 25 years, so quarter of a century experience in AI. And quantum computing looks very much like when I started with AI. So there is the first hype, but it still not has reached adoption of like what we have nowadays, machine learning. Everybody calls AI, everybody like in the dark is knowing AI, using AI. However, I believe that one of the next big things will be quantum computing, and which is why I believe that it's a way to go for IONOS to also work on providing a quantum cloud solution. So to give you a context, what IONOS is, we are a leading European cloud infrastructure and hosting provider. So whatever you need, like managed Kubernetes, managed databases, storage, you name it, we have it there. You might have seen yesterday the keynote of our CTO. In the end, we are a innovation-first company, which is why we are also currently investing a lot in current, let's say, trends, which is AI, however, as well in quantum computing, where I want to show you, together with Georg, our journey, our baby steps into kind of like the contribution to the democratization of quantum computing. So for me, as somebody working for IONOS, in the end, the journey is relatively easy in providing quantum computing to our customers, as long as we can kind of like build on the shoulders of the giants that are really knowledgeable in quantum computing. In the end, when I talk with our quantum computing partners and ask them what the customers are requiring related to quantum computing, it's all about the same thing that I've heard already about cloud computing. So what they need is, for instance, cybersecurity. In the end, you have your data, and this data is very crucial. You don't want to get it lost, compromised, stolen, whatsoever. And that's why it is very important to have cybersecurity, data protection, and also compliance in the European, let's say, area. In the end, that's what is some of the DNA of IONOS. So that's rather easy for us to provide. However, there is one thing that is rather crucial, and that's data sovereignty. In the end, data sovereignty means, I mean, it has been already probably named several of times, this buzzword, let's call it a buzzword. It is about retaining control over your data. And here, I mean, really not losing any control. So as a customer, the best way you would like, if you want to use a quantum computer, you would like to have your quantum computer on-prem in your own data center. Not possible yet. Hope soon the technology will be advanced far enough that you can do this. So you need to rely on some central platforms where you just hand out your data, and then you have to trust that the provider is really treating your data confidential, properly, that nothing is lost and nothing is stolen during the whole process. And here, that's what we are currently working very hard in this segment on data sovereignty, in the sense that you keep your data on your device, on your storage, on your data center, if you like, and then you just stream for the computation to the cloud, to the central platform. The data is being processed, you get your results. And that's what we are working on in quite a few research projects. So when you look, there is just a small portfolio. Everything is just, all of those projects, let it be IPSAI CIS, nowadays called ERA, where we want to strengthen the European digital sovereignty, or lots of projects in different direction about data spaces, Gaia X. That's what we are working at. And one of those projects where we are engaged is Sequency, which is exactly the goal to create a sovereign European quantum cloud where customers can just send their data to a cloud provider, getting that processed. I mean, in the end, for us as IONOS, as a cloud provider, it makes sense since quantum computing is always hybrid, so you have load of traditional classical computing, some of the load that can be really efficiently computed via quantum computing. So you have this kind of like a partnership, and that's where we are in this project. So this is little bit our, let's say, the architecture, very high level the architecture, what we want to achieve with our project. Currently, we already have a quantum computing node, which is more a simulator, but also quantum access node. Here in our Berlin data center, that comes from QMware, where Georg will soon give some more details. And in the end, on top of it, the customer is in the center, and it doesn't matter how knowledgeable they are in quantum computing, they should have different type of access. So it doesn't matter. You may want to really write your quantum, let's say, algorithms in any quantum framework. No problem. It's fine. You can just do it, send it over an API, and then it's being processed on our cloud. Likewise, you might want to have some more high-level programming, like you might have seen, I think it was yesterday, there was Fraunhofer Focus presenting CRISP, which is a Python framework which makes it way more easier to write quantum programs. So even like easy for me, who's a classical, let's say, programmer, to make it possible, no problem. Also, it is already integrated, the Sequence API in CRISP. Maybe you don't have any idea about how to do quantum computing, so you could want just to use ready-made algorithms. And in this case, you either can use the workflow modeler or even some ready-made applications where you kind of can access the capabilities of quantum without really knowing how to do this. In the core of it is, I mean, everything is running on the cloud. Everything is then executed on different QPUs. But in the core of it is a unified quantum hardware access layer that translates then to either simulators, quantum simulators, or to different QPUs, which allows you to have some, well, unified way to access quantum computing capabilities. And this core technology is among others, being provided by QMware. That's why Georg now will go into the technical details about this part.
Thank you, Lukas. It's really great being here. And yeah, my name is Georg Gesek. I always wanted to know how the universe works. I cannot tell you how far I proceeded with this endeavor, but since then I realized the whole universe is merely a quantum computer, and for that reason we are helping to build and utilize and commercialize quantum computers, which is a fantastic task. And as you can see here, a quantum computer will not replace classical computers, not for the foreseeable time, but they are an extension to classical computers, and there will be an intriguing presentation, I'm sure, from Laura Schulz here in 2 p.m. And what we are trying to do and what we have achieved is to unify the access for different types of QPUs. And you can imagine quantum processing units are very, very different. They are built in laboratories, and you need really the most sophisticated scientists to build such QPUs, quantum processing units. So quantum computing is not rocket science, it's much harder. And yeah, you can imagine that every flavor of those qubits is very special. So what you need for the quantum chip is to have a translation between quantum and classical resources. So you have quantum information on one hand, and you have to create this quantum information based on what we have in space-time, which is classical information. We think, we live in space-time, which is classical information, classical physics. And so you have to prepare the states for the quantum computer, for the quantum register, so to say. And then you have to impose a quantum circuit or some other parameters in order to get the machine prepared for doing the task you want to do. Because a quantum processor is nothing else as a small universe, I said, where you imply your laws of nature. And those laws of nature should replicate the solution for your problem you want to compute. So then you have to measure the whole thing. Yeah? And the measurements will be retrieved into a classical computer because the measurements, again, are classical information. And you need this quantum runtime environment to get over the whole platform, by the way, so for the classical and quantum resources in order to get the programmers and the software engineers and the application engineers able to use hybrid quantum computing. And everything you see here is leveled on one standard, which we call a quantum hypervisor, which for the first time from QMware, what we are providing and promising to our customers is that our quantum hypervisor in the instruction set is downwards compatible. That means software implemented today on QMware's quantum hypervisor will run indefinitely. It's like an x86 platform where the software from the 1980s still running in our data centers. And this is important for investment security for the industry. On top, you have different compilers. We are closely working together with NVIDIA on that. So there's QReQuantum. Our quantum hypervisor is using QReQuantum and extended it with Cognite to the different types of quantum registers and QPUs. And obviously, there is much more. You have a full hybrid quantum computing stack where you not only have the hypervisor in order to access all these different types of quantum processors, but you have also to integrate these systems, which consists of hardware and software and very costly hardware, by the way. So you need for one node, for one memory-centric compute node in hybrid quantum computing, you need CPUs, you need GPUs for pre- and post-processing, and you need the QPUs. And altogether, it sums up to several millions of euros nowadays. So we hope this level of investment gets down. But if you think about one GPU, for example, in the high-end market, it's as costly as a mid-range car with all the options. So it is not cheap to implement high-performance computing nowadays on so-called heterogeneous processing architectures. And quantum computing is nothing else but the further development of heterogeneous computing architectures or modular supercomputing. And that means that all the industry cannot waste time and money to get prepared and to adapt to their applications to hybrid quantum computers. We from the quantum computer industry have to do that for them so that they can use their C++ libraries, their applications, and as Lukas said, just change the way how to compute, change the way how to process algorithms on those new types of machines, where we are talking about kind of a Stargate. Yeah? So you have an application, you are sitting in the IONOS cloud or in any other cloud provider's cloud, and this application tunnels the hard computational tasks to a backend, which is somewhere, the backend costs hundreds of millions, and it sits somewhere, and you can then retrieve the solution of real hard problems, or you can retrieve the solutions for large language models to learn. So again, quantum computing is not a contradiction to classical supercomputing. It's a natural part of it, and in future we will extensively use that. And you can use it for all the hard computational tasks you have today in AI already. And that makes it a very smooth transition, commercially wise, from the AI and high-performance computing, which we are now deploying very much, to hybrid quantum computing for the same applications on the same architecture of software. So this leads to the exploitation of really great use cases. When I say great use cases, I'm talking about a broad variety of use cases in nearly all the industries, especially when it comes to infrastructure, which is out there, which is very costly. Like, for example, in the aerospace, you have satellites. We have made a POC. We have made over 100 POCs, by the way, so you can ask me later on for each. I remember. So more than 100 POCs with the industry on a global scale for hybrid quantum computing, and we can literally tell exactly the point when it comes into fruition in a commercial sense. So 2/3 of those use cases showed a quantum computing technical advantage. We are now trying to get commercial quantum advantage so that the infrastructure, which is so cost intensive, is paying out even for the use case. And the use cases, if you have several billions invested in your satellites, a few % of using them more efficiently will pay you off for large scale infrastructures on hybrid quantum computing. Okay, so this should have given you an first impression of the close in the future, the near-term applications and the near-term approach of hybrid quantum computing based on a unified compute architecture. And I thank Lukas, I thank you all, and have a great day.